So we spent quite a bit of time modeling individual components and then putting our mechanism together so that it works. But really, we might often start out with just a conceptual idea of what we want our model to do. And so before we generate any physical geometry, we could set up a schematic or stick figure of what we want to do. And so here I have this lift plate that I want to go a certain distance. So I'll animate the model. So we see that that goes up and down to the scissors lift up the plate. So we can set all this up and get it working, and then go to the trouble of modeling our components. Now we've got our components modeled though, so I want to do an analysis of how much force would be required with my hand at different positions along this handle to lift a load placed on here, let's say 1,000 pounds. We don't lift the entire car, but only one corner of the car at a time. And so we'll say 500 or 1,000 pounds that we want to lift, and then how much force is required our hand to do that. Now we can't do that analysis in Fusion 360, so we'll have to go to Inventor to do the analysis there. So I'm going to export my parts first, and I'm going to save these as a step file, and then we will put it together in Inventor and run the analysis. I'll save it and then open it in Inventor. The first thing I do in Inventor is I create a project, and then I'm going to go to open up that step file. So I'll have to set my file types to step, and I'll open up the scissor jack. I want to convert the model, say OK. Looking at the view cube, I want to reorient the top view, and so I'm going to select the view cube and I'll set that current view as top, and then I also want to set a home position, so I'll orient it how I want, and then I'll set that current view as a home position at a fixed distance. Alright, now we see that the first part is actually the lift plate, and I would like for it to be the base. So I'm going to drag the base above the lift plate, and I'm going to ground the base. Okay, so I'll set that base is grounded, and then all of the rest of our components can be moved. So the assembly constraints from other CAD programs are not preserved when you export that as a step file, and so we'll have to go through and put these individual constraints on our components. Now I'm going to unground the lift plate, and I'm going to expand the base origin and the lift plate origin. I'll do constraint, and you can either come up here and do constrain or C for constrain, and I'm going to do flush the YZ plane of the base to the YZ plane of the lift plate, and then I'm going to do the XZ plane of the base to the XZ plane of the lift plate. So now we have 1 degree of freedom translation. So we don't have any other components connected to this. So in a sense, we are cheating a bit in the CAD world, but since that will simplify our calculations, we will do that. And if we go to dynamic simulation, we would expect to see a prismatic joint for that lift plate, and that is in fact what we have. All right, then I'm going to put these pins into the base, and so I have the base expanded. I will find these pins, and so here's a lower rivet here, and there's also a lower rivet here. We'll do these one at a time, so I'm going to expand that. And now we could just ground those. Since they came in position, we could just ground them, or we could put some constraints on them. We'll do the constraints up here on this one, so these two will just ground those. So I'll ground this with the 2 lower rivets, and then we'll constrain these 2 rivets up here. So I'll do constrain, and I'm going to put it on flush, and I will do I need to expand those over here, so I'll find those 2 upper rivets. I need to do the XZ plane of this rivet to the XZ plane of and I'd prefer to do that to the lift plate. And so those are lined up, and then I'll do mate, and I'll get the axis of this pin, and I'll get the axis of this hole, and I'll apply that, and then I'll find the second upper rivet, and I'll do the XZ to the XZ, and then I'll do the axis of this pin to the axis of this hole. Alright, so now if I test this, those 2 pins move with that plate, and then I'm going to constrain this arm. So I'll find the base and I like to move these grounded parts up together. So I'll move that grounded lower rivet and this grounded lower rivet. I'll move those two together, and I'll expand then the origin folder for the base. I'll find the lower left arm, I'll expand that origin folder, and I'll do constrain. I'll do flush the XZ plane of that arm to the XZ plane of the base. And when I did that, it flipped it around, and so I'm going to put it on mate instead of flush. And so now we see that it's in the correct orientation. I'll do apply to that, and then I'm going to put it on mate, make sure it's on mate. I'll select the axis of this pin and the axis of this hole, and we'll say okay to that, and we test this out, and we see that this arm moves. We'll do the same thing over on this side. So I'll expand the lower right arm, and I'll do constrain. I'll put it on flush, the XZ of that plane to the XZ of the base, and then we'll put it on mate, this axis, and we'll say okay to that. Now we would expect that there would be two revolution joints for these two arms. If I go to dynamic simulation, we see that we have those two revolution joints, and then I'm going to constrain this arm to this arm. So I will find the two left arms. So here's lower left and here's upper left, and I'll do constrain. And I don't know if this is going to be flush or mate. Since we flip this around, I'll assume it's going to be mate. So I'll do the XZ plane of this arm to the XZ plane of this arm, and it's oriented correctly, so I'll apply that. And then I'm going to do with mate, I'll do the axis of this hole to the axis of this hole, and I'll apply that, and let's just cancel out and test that out so everything still moves. And then to put it up here, we've already got it lined up where it doesn't translate. If we put a axis to axis up here, we're going to get an overconstrained condition. So rather than axis to axis, I'm going to do point to axis. So that allows 3 rotational degrees of freedom and 1 translational degree of freedom. But of course, because we have the revolution joint down here, it's not going to translate, but it allows that rotation for clearance between this hole and that pin. So I'm going to do constrain, and I will select this axis of this pin, and I'll select the circle, which will find the center point of that circle, and then that should give us a point line joint. So if I go to dynamic simulation, I see now that I have a point line joint here. Now we can just put these joints in while we're in dynamic simulation. We can go to the assembly view here on the browser, and I will expand the right arms. So here's the upper right arm and lower right arm, and so I'll do C for constrain, and I will do flush, and I'm not sure whether this one's going to be flush or mate. I think it's going to be mate, so I'll leave it on mate. The XZ plane of the lower right arm to the XZ plane of the upper right arm, and that's still oriented correctly, so I'll apply that. And then I'm going to do the axis of this hole to the axis of this hole, and we'll say okay to that, and we should have a revolution joint. If I go to the dynamic simulation browser, we now have a revolution joint for this component. And then we'll do the point to axis. So I'll do C for constrain with it on mate. I'll select this axis, I'll select this point, I'll say okay to that, and that should put a point line joint in here, which it did. And then we'll constrain this component, and I want to center this in the assembly, so I'm going to use the plane that goes through the middle of this, and the plane that goes through the middle, we'll use the base. So I'm going to expand the screw assembly, but I'm going to expand the origin, and I will do C for constrain. Actually, I want to find the part down here and use that as the part that I use for the constraint. Okay, so that's actually, I need to find the correct part. This one is grounded in that subassembly, so I'll use it. And so I'll do constrain that component or that plane to the base, XZ of the base, and we'll say okay to that. And then I'm going to do the axis of this to the axis of one of these holes, and we only need to do it on one side. Now I'm debating in my mind how I want to do that, whether I want to do point line or an axis. We'll go ahead and put in the constraint. We can go back and change this. So I'm going to do the axis of this cylinder to the axis of one of these holes. I'm going to use the hole for the bottom arm. Now I was expecting it to pop up into place, and it doesn't pop into place, and I look at these two arrows and I see that they're going in opposite directions. So I'm going to do aligned, and that didn't work, so I'll do undirected, and that still didn't work. So so I've got a mistake in there someplace that I'm going to need to find that mistake and fix it. I think if we do this in the opposite order, we'll see what the problem is. So I'm going to finish dynamic simulation, and I'll go to the relationships folder, and I'm going to delete that last constraint that we put in here. I think I'll just suppress it for now, and I'm going to put the second constraint on here between the axis of this and the axis of the hole. So I'll do the constraint, I'll select this axis, and I'll select the axis of this hole, and we see that it moves into position. Okay, then if we unsuppress this constraint, we get an error that won't work. And here is the reason why. We constrain to the plane that is in this component right here, which isn't necessarily lined up with this component. And so even if it was lined up, what we need to do is make this subassembly flexible. If we try to rotate this right now, notice that we can't rotate it. And so I will right click on that subassembly, and I'll set it to flexible, and we see this symbol here. And now I'll right click and I will unsuppress this, and now we didn't get the error, so it worked okay. Actually, because we don't have these components constrained within the subassembly, remember we brought this in from a step file, we have to go through and constrain the subassembly as well. And so let's open up that subassembly, and so if I move these components, we see that they move around. I will then do constrain, and I'm going to use insert as a quick way. So I'll insert this circle to this circle, and I'll insert this circle to this circle, and I'm going to insert this circle to this circle, but I'm going to end up putting an offset distance in. And let's flip that back that direction, and I don't know whether it'll be negative or positive. Let's try a 0.5, and that's the wrong direction, and so I'll do negative 0.5. And so I put it a little bit past middle, but this could slide back and forth. Let's do 4.5. And that looks pretty good. And then I also want to constrain this so that this handle cannot rotate from side to side. Let's undo back to where that was. So I'm going to do an angle constraint between, I think I'll use this face and this face, or I could use the planes within those components. So I'll do constrain, and I'm going to do angle, and I'm trying to decide how I want to do this angle, and I'm going to put it on directed angle between this face and this face, have it at 0 degrees, and now that handle can't rotate back and forth this way. All of this can rotate in this direction, and then this can also rotate. Alright, I will save this and go back to my assembly, my top level assembly, and I'll click the update icon. Everything updates, it's into position now, so this geometry is okay. And then I'm going to constrain this component in here, and so I need to find that component. I'm going to center it using the base, and so I'll band the origin of the base, and then I need to find the nut, and I'll constrain. I'm going to put it on flush, and I'll select the XZ plane of the base and then the XZ plane of the nut, and then I'll put it back on mate, and I'll get the axis of this to the axis of this. If we test this now, this should be able to rotate. We might need to ground one of these components so that we could test it rotating. Let's go back to dynamic simulation and make sure that we don't have any overconstrained conditions. So I'll go to environments, and I'll go to dynamic simulation, and we have an overconstrained condition, so we need to figure out how to get out of that overconstrained condition. Now this might not fix the issue, but I see that the problem that Inventor is indicating to us is between the clearance rivet and the screw clearance washer. I would like Inventor to treat all of these components as this component and this one in the handle as one component, and then that is a separate component. So we'll see if this will fix this. I'll finish dynamic simulation. I'm going to open up the screw subassembly, okay, and then I'm going to set these three components as all grounded. Let this one rotate. I will set the screw to grounded. Within the subassembly it's grounded, and then within the subassembly the handle is grounded. So the only component that can rotate is this component. Now we could have done it the other way around. We could have let this component grounded and then put all of these, though that would be a lot more work. And so this will be the easiest way with this component can rotate. Alright, we'll save that. We'll go back to our main assembly and hope that that fixes the situation. So I'll go to dynamic simulation, and we see that it's still over constrained and it's still a revolution joint here, so we'll have to figure out a different way to do this. So in trying to diagnose the issue, I grounded the lift plate, and if I try to rotate this component, it doesn't rotate. And so then I realized my error. I have a mate constraint between the screw assembly and the base that will not allow this to rotate as long as I have that constraint in there. So I need to remove the constraint between the screw assembly and the base, so I'll delete that. And so now this can translate back and forth, but rather than the screw assembly, I need to put it to the plane on this component. So I'll go to the origin of the screw clearance rivet and I'll find that constraint. So constrain this plane to the base XZ plane, so that moves that over into position. I'll try to rotate this now, and we see that that now rotates. And so even though in the subassembly, if I go back to the subassembly, those components are grounded, but when we put those into an upper level assembly, because of the degree of freedom that we have here, those can rotate with it set to flexible. Alright, so now we'll go back to dynamic simulation and see if that fixed that error. So I'll go to dynamic simulation, and I left the lift plate grounded, so I'll have to go back and unground the lift plate. So I had temporarily grounded this so that I could tech this component without everything moving. So I'll right click, I'll unground the lift plate, and then we'll go back to dynamic simulation. And this time I don't have any over constrained conditions. Now one problem, or one thing that can cause confusion, is when I go back and forth like that, the joints may have been renumbered, created in a different order. So your joints numbers may not match mine, but the joints themselves should match mine. So our biggest issue, or our biggest problem when we get to more complex assemblies, is to avoid over constrained conditions. We'll spend more time trying to figure out a strategy for putting our assembly together to avoid redundant constraints than probably anything else that we do. And that is especially true for the next constraint. You should spend some time trying to put on the next constraint and stop the video and then come back and see how I do it. So it's a real challenge to get that next constraint on here so that it is not over constrained. I've had students come up with a couple of different solutions that basically end up being equivalent. If we think about this, we want any point on this plane or a plane in the middle of the part to be lined up with any point on this plane. Now we need for that point though to be able to slide mathematically back and forth across this plane. So we can't do plane to plane or flush or angle. We need to allow that point to slide actually an axis. Those planes have to be lined up. So we'll select C for constraint, and we'll select an axis on this plane that is along the axis of the screw, and then I will select this plane and it moves that into position, and we'll say OK to that, and it gives us a line plane joint, and it is not over constrained. Next I'm going to set a home position, so I'll finish dynamic simulation, and I'm going to go back, and if I pull this down, at some point this component right here would hit the bottom of that component, and so I'm going to put a tangent at that position. So I'll do a constraint, and I'll do tangent this plane and that cylinder, and I'm going to name that as home position dash suppress this. Of course that would lock it into place, so we'll end up suppressing that constraint. So I'll go to my relationships and I'll suppress that constraint. Alright, and then I want to set up to put a load on here, and in order to do that I'm going to need some points on this part. So I'll shift right click and make sure I'm on part priority, and I'll open up this component, and then I'm going to do a point at a center loop of edges, and I'll do a point at the center of this face, and I'll do another point at the center of this face. I'll save this file, go back to my main assembly, and then I want to put some points along here for a location where I will put a load. And so I'm going to open up this component and go to a side view, and I need to decide where I'm going to put those points along here. So I'm going to do a sketch on this plane, and I'm going to project the edge apart. And then I could either put the points on this side or this side. It doesn't really matter. I guess I'll put them on this side. And if we do a FEA analysis, actually, if we're pushing against this curve or pushing away from that curve, it might actually make some difference, but I haven't tested that. I'm going to put a point about right here, and let's dimension that location from here to here. Let's say that's 2 inches. And I'll finish that sketch. So that was a sketch point. I'm now going to put a work point at that location, and I'm also going to put an axis at that point perpendicular to this face. And I'll turn off the visibility of the sketch. I might make this axis a little bit shorter, and I'll pattern this point in this axis. So I'll do a rectangular pattern, and I'll select both the point and the axis. And for the direction, I'm going to do that along the y-axis, and I'm going to flip that direction. Do, let's say, 3 copies. Let's do those 2 inches apart. Okay, so that's going to represent placing my hand here, or placing it here, or placing it here. I'll save this, and I'll go back to the assembly. I'll update my assembly, and then I'll go back to dynamic simulation, and I'm going to put a load on here, a total of 1,000 pounds. So when we're lifting up a car, we're probably only lifting about 500 pounds, but this jack is supposed to be rated for 1,000 pounds. And so I'm going to put a force at this point and at this point, and I have to do these separately one at a time. So I'll do 500, and for the direction, I'll select this face, and I didn't get that direction set correctly. Flip that direction, and I'll do the 500 pounds here as well. Alright, then I'm going to put a force on here, but I don't know what force would be required to lift up the 1,000 pounds. And so I'll do an unknown force, and I'm going to do this relative to this prismatic joint. And you may want to flip the direction on the prismatic. I think I want it going up, the z-axis going up. If I need to, I'll flip the direction going to the other way. Alright, so I will then do unknown force, and for the location, I'm going to put it at this point, and for the direction I will select that axis. But as it goes around, that force is going to change. It's going to go around in the circle here. So I don't want this as a fixed direction. I'm going to tell it to do an associative load direction. And then rather than relative to the revolution, I want it relative to how high I lift this, and that is the prismatic joint. I can see that right now its initial position is 2.6 inches, and I'm going to add a value to that. Let's say I want to go up an additional 8 inches, so I'm going to say 10.6. Now it's probably best to just do it a short distance first, and then make sure everything is working okay, and then you can increase that distance. And I think I want to flip that direction, so I'll flip the direction so that it's pushing it this way. I'll say okay to that, and it says that it has 2 degrees of mobility, so I need to lock a degree of freedom in one of the joints in order to get this to work. So I need to find where I've made that mistake. So I forgot to put my screw joint on here, and so we'll do insert joint, and we will find a screw joint, and it wants us to select component number 1 and component number 2, and it may be important how we select these. I'm going to select this circle on this component, z-axis going this way, and then I'll do second component. I'll select the circle on the end of this screw, and I'm going to flip the Z on that one, and I prefer to have the X lined up if we can get those lined up. So this is X, that's as close as I can get it. And the problem is the teeth might not be lined up, but for what we're doing, we're not doing an analysis between the teeth, so that doesn't matter. And then for our pitch is 0.1, and we'll say okay to that. And then we will do the unknown force. So I'll go to the unknown force, and I want to get that at this location, and I have it on associative, prismatic, and I want to slow this thing down, and I can slow it down by increasing the number of steps. So let's do 1,000 steps. Now that might be too slow. We might have to decrease those number of steps, but let's say okay. Now if it starts to go the wrong way, if it starts to go down, I'll immediately stop. So I'll say okay. And we see that it's going up. I also may have set the height that I'm moving as too far. We'll see. Notice as it goes higher, it rotates faster and faster, but the amount of lift is decreasing per revolution. So we see that if I search max on the force, at the beginning we had to put in about 13 pounds of force, the user, in order to start to lift the car, or the 1,000 pounds. And then as it got higher and higher, the user puts in less force, but they have to turn it more revolutions in order to get the same amount of lift. And let's put the lift down here instead of step number. So I'm going to right click on position, or set that as reference. And actually I have to unselect it before it will let me set it. There we go. It put it. No, I have to unselect it. I don't want it to display the curve for the lift. So at the beginning we see it was the home position. This was already about 2 inches above the ground, and then we put in about 13 pounds of force, and then as we lifted the plate up higher and higher, the lift plate, the amount of force got less, but we increased the number of revolutions for the lift. So you can do the same experiment by placing your hand here, or placing the force, the unknown force here, or the unknown force here, and you'll see that as you move closer to the center of rotation, you have to increase the amount of user input force. And of course, in the real world, as you're turning this handle, you have to realign this handle because you can't go through the ground, but we can ignore that as we are doing our analysis.